If you've heard of Ed Lorenz and his ideas on chaos, which became a prominent field of study into many fields, then you probably heard of the idea of predictability of the second kind, which is essentially extending from weather timescales to climate timescales, where the idea is that if the initial conditions had small errors, then weather prediction can get very large errors very quickly within a few days, so there is a limitation for weather predictions. Then how is it that we can make predictions of El Nino and other seasonal and longer time scale events? The idea is, of course, that the atmosphere is has very low heat capacity, basically no memory. So if you think about time horizon here and predictability here, in some way predictability, let's say intuitively think of it as the ability for us to predict something. So the atmospheric processes predictability drops off very quickly in a few days. You can say here it drops off by 7 days, and then there is some level of predictability beyond which the information is not very usable. For example, if you're making a prediction of rainfall consistently at 30% skill, then it's not very usable. Above 50%, maybe you can begin to make decisions under uncertainty and so on, right? So the heat capacity is low, and then land comes in next. At very short time scale, it has no predictability, but because of soil moisture and other properties, it begins to have some predictability up growing to 7 days peaks, and then begins to drop off again because there is memory in the system, again related to heat capacity, right? How long can it keep the cold and the heat that's in it, so that when you integrate you can track it. Ocean at the very short time scale is not changing much, but slowly over time scales of months and longer, it begins to have memory. So if you think of sun being in the southern hemisphere for 6 months, northern hemisphere for 6 months, the ocean is soaking up heat in the southern hemisphere for 6 months, and then when sun moves north, it begins to give up that heat, because ocean is several kilometers deep and has very high heat capacity compared to land and atmosphere. It can provide these slower time scales. So the evolution of land and atmosphere in that sense begin to get modulated by the slow variability of the ocean, and that's what gives us additional predictability beyond the weather time scale. So weather is done, as you remember we briefly said, without allowing the ocean to change. Land also mostly is prescribed in many ways, let's say land ice and so on, or atmospheric chemistry and so on, or land chemistry as well, vegetation for example. So that's where the predictability of the second kind comes in, and that's where our predictions of El Nino and so on have some skill. So this is just a statement from the book. Is it either or? Think of weather prediction problem, because you are integrating only for a few days and typically you are focused on making prediction for a particular country or a particular region of a country. The idea of representing the grids or the sphere as a grid can be used to make it very high resolution, or many more grids, so that you can represent smaller scale processes like clouds and rain at regional local scales, but computational cost of that is very high. But since you are integrating for a very short time, it doesn't matter so much. So typically NWPs, or numerical weather prediction models, are run at high resolution, whereas climate models, which have to be integrated for weeks, months, and even seasons, typically are run at a much coarser resolution. So the idea was that the climate models don't have to capture the weather processes like fronts and blocking patterns and so on. In that context, conversely, there is a growing interest in the climate community to better represent mesoscale weather events. Mesoscale is generally medium scale, so it's neither planetary scale nor very local scale. It's a scale at which some weather patterns evolve and happen. In long-range simulations, we want to capture some mesoscale weather events. This is for two reasons. A good representation of weather within climate, synoptic scale events, can feed back into a better representation of the large scale climate. Okay, specifically for El Nino, for example, the short synoptic scale weather wind anomalies determine how quickly and how quickly El Nino grows and how strong it may get. They're called westerly wind bursts, which we won't get into, but you can go and see other podcasts on that under El Nino. Okay, being able to represent synoptic scale events may allow the direct prediction of impact of climate change on the statistics of weather. Okay, like cyclones, for example. If climate models are not representing cyclones, but they want to make projections of how cyclones will change next year or in this season, how many cyclones we will have, the cyclone related weather patterns like vorticity, wind shear, vertical motion, humidity levels, ocean heat content, etc. have to be included. Okay. For instance, this would help answer the question such as, will global warming impact the number and severity of winter storms over Europe? Okay, so oops, sorry, I didn't mean to do that. So the idea of what is called now seamless prediction is evolving, where same model can be used from weather timescales to climate timescales. Whole host of issues there which we won't get into, but in the meantime what we can do is look at the prediction timescale and method. So weather timescale is done with atmospheric general circulation model, which solves the primitive equations for momentum, energy, thermodynamics, continuity, and so on. So the atmosphere is allowed to evolve as shown here in the blue color, but these orangish colors are fixed or prescribed. So ocean is prescribed in terms of sea surface temperatures, for example, and atmospheric composition like aerosol loading, chemistry are prescribed. So only the atmosphere is evolving in time. The seasonal forecasts, how will the winter look, how will El Nino evolve, and so on, are done by allowing the atmosphere to evolve, but ocean is predicted ahead of time, and for example evolution of sea surface temperatures is given, and then atmospheric response to that is allowed to evolve. So there is a evolution that is prescribed. It's not fully evolving, and then atmospheric composition may be still fixed. So these evolutions of the systems can be thought of as internal variabilities. They are changing because of the changes in radiation, internal nonlinearities, and so on. Actually, radiation is an external forcing in the sense of coming from the sun. Let me not get into it right now. But these components that are prescribed can be considered as external forcing. And in a single tier seasonal forecast, both atmosphere and ocean are fully evolving, so they are integrated together. Ocean evolves, atmosphere evolves, again ocean evolves, and so on. Whereas atmospheric composition typically is prescribed, but now there are many so-called Earth system models which are used, for example, for projections, two-tier or one-tier. These are terminologies where sea surface temperatures are partially fixed or completely evolving, and similarly here atmospheric composition is partially prescribed or fully evolving in response to human land use, deforestation, agriculture, urbanization, etc., transportation, and so on. Okay, so this is the way to think about it. Which component is evolving, which component is prescribed, and what is internal variability given the radiation at the top of the atmosphere? What is the system determining by itself, and what are the things that are being prescribed, and so on. So using these kinds of ideas, El Nino prediction is really the poster child for seasonal to interannual forecasts. This is the latest forecast for 2021, made in mid-April. The next one will come out soon, as I'm recording this in the second week of May 2021. So you can see that for the April, May, June of the following months, there is a high probability of neutral conditions from multiple models used in this. This can be done by combining multiple models which are typically coupled, or they are statistical. we will not get into details. Let's assume they are coupled atmosphere-ocean models. So both ocean and atmosphere are evolving with atmospheric composition fixed. And as you go into the future, into August, September, October, and December, January, February of 2021, you can see that the probability of a La Nina increases a little bit. So does El Nino, but the highest probability is still for what is called ENSO neutral year. So it will be neither an El Nino nor a La Nina. So this is typically how forecasts are issued, and then various sectors, depending on whether it's a bank, government, resource managers, fisheries, agriculture, stock market, weather derivatives, they all tend to use this information and make decisions under these probabilistic informations. This leads to what is called unified model seamless modeling hierarchy. This is example from the UK Met Office. So here are forecast lead times going from weather timescales to climate projection timescales, and the resolutions as we talked about, and the scales, regional, what is the status of the model, and global coupled Earth system, which means it includes various carbon cycle, vegetation information, atmospheric chemistry, ocean chemistry, and so on. So you can see that the same model with various configurations is being used, or is being proposed to be used. US is doing a similar thing. These are called seamless basically because they go seamlessly from weather to climate to forecasts, predictions to projections, timescales. Okay, lots of details there that we will not get into, but we will talk about the evolution of S2S timescales during this whole weather and climate prediction. So weather predictions have been happening for decades. ENSO prediction has been happening for a couple of decades, and then sub-seasonal to seasonal has now evolved, and we will see how that comes about and what other timescales are evolving along the way.